Cool. Bobby just paused me and just told me something interesting. I want to make a quick clarification. These energies are not these actual functions here. These energies are listed in the notes. So E1 is h squared over 8ma squared, E2 4h squared over 8ma squared, and so on. So combine this picture with what you see in the notes to see the full image. Thank you, Bobby. Okay. Now, we're going to move on to the harmonic oscillator. And I'm going to talk while I'm erasing just to expedite time. So the harmonic oscillator, if you think about two masses connected to a spring, think about what that spring is doing. We had, with the particle in the box, we had our particle hit the boundary of that wall, and depending on where that boundary was, affected what the wave function could be. So now think about a mass on a spring. That spring constant, is going to be limiting the distance at which that mass can go back and forth. So for the harmonic oscillator, so you've got mass 1 and mass 2, both connected on the spring. So this is going to be some distance between them. Now this is the equilibrium distance. And so if I were to stretch that spring out to some now new distance r, so it's stretched, there's going to be some, now the goal is now to determine which wave function is going to incorporate the boundary conditions that originate from, now it's not being contained within a box, it's being contained from within this spring. And of course you can hopefully see where we're going, that this is going to be our representation of the wave function for molecular vibrations, which are also quantized. Okay, so if you take this mass and you stretch it out, there's going to be a restoring force associated with the displacement. So you've got x is equal to r minus r of the equilibrium, where this new stretching, so this r, then r equilibrium, is equal to your x. And then the restoring force f of x, or sorry, f in the x direction is equal to minus kx times the displacement. And so this is your spring constant, soon to be the force constant associated with the strength of the chemical bond. And then this is just the force that you have between them. And this is negative because it's going to be going, it's a restoring force. So I have a nice note that this is Hooke's law from 1635 to 1703, and FYI, Hooke was a student of Robert Boyle, the wonderful one who started with the ideal gas law. Okay, so here's the kicker. When we had the particle in the box, we didn't have a potential energy. Now, however, we have a potential energy, and you already know what it looks like. Let's put it down here. So if I were to ask you to draw the potential energy of two masses on a spring, you would hopefully draw some sort of parabola, where you have zero potential energy here, or sorry, zero kinetic energy here, so you're at equilibrium, and then you have an increase in potential and a decrease in kinetic energy, and back again, and an increase in potential energy and a decrease in kinetic energy because it's slowing down to where when the spring gets to where it's stopping, so it stretches out and then it stops, it has zero kinetic energy and all the energy is contained within the potential energy of the spring, and then there's that restoring force back. So we have the potential energy is equal to 1/2 kx squared. Oh, sorry, kx, which is our x or spring constant in the x direction, times the displacement squared, which is just the negative derivative of the force. And then we've got our kinetic energy, which is equal to 1/2 mv squared, or I'm going to put this in terms of momentum in the x direction, px squared over 2m. And in the notes I explain how that relates to the velocity. So the classical treatment is to look at the summation of the potential and the kinetic energies, just add them together, and that gives you your total energy. However, remember we're quantized, and the only way to get the total energy is to operate on whatever wave function is going to represent the boundary conditions of this particular system, psi of x, to get E psi of x. So that same handle that we had to turn with the particle in a box, we are still going to have to turn that with the harmonic oscillator. But now we have a potential, so that makes it a little bit more tricky. So what I'm going to do is I'm going to still use the Hamiltonian. And so here's my Hamiltonian down here. So now I've got minus h bar squared over 2m d squared dx squared. Now what is my potential? Well, right there, plus 1/2 kx x squared. So how do we solve the Schrodinger equation for now this added potential energy? Well, we don't. This is one of those horrible times that I wish I could help you out in solving this, but we're not going to solve it together. I'm just going to give you the answer, but I'm going to kind of hand wave the arguments as to why we need a particular type of function. And it involves what are called Hermite polynomials. Okay, but we'll get there in a second. So to solve, h psi is equal to e psi. What we're going to do is we need a different wave function than the 1D box, but what we need are specific conditions. So number one, we need psi to go to 0 more slowly at farther displacements. Basically, it needs to slow down. It's not actually quite correct to say it slows down. But what happens then, let's come back over here. So what I'm going to turn this into, the classical the classical spring is going to have all of these allowed energy states. Not the case for the quantum mechanical spring. You're only going to have very discrete energy states that are allowed. And what's going to happen is that the boundary here, so at very small displacements, psi is still fairly large, but at larger displacements, now you still need psi to go to 0, but you need psi to go to 0 right here at this boundary, but then when you get up to the higher energy state, you need it to go to 0 at a slightly larger value. And so that's what this number 1 says. Okay, whereas with the particle in a box, let's see, unlike there's a particle in a box, it has to be 0, always 0 up here or 0 up here, or up or down, either or, it still has to be 0. Where now the height of the box that is representing where the spring is actually going to make an effect on what psi has to do. Okay, so that's the first condition. Number 2, the larger the mass, the faster the decay of psi. So psi has to go to 0 quicker if you have a large mass on the spring. And so what that means then is if you have, say, hydrogen gas, you just have 2 hydrogens, that's not going to have the same wave function representing the spring or the molecular vibrations as, say, hydrogen chloride, so HCl. Okay, and number 3, the box has to widen at the top, which means that there are larger energy states, so you need a broader psi. So over here, you have psi that looks something like this, but now, when you come up here, whoops, you're going to have, so now psi has to actually spread out as you get to higher and higher energy states. And so the box widens at the top, or for larger energy states. And I will say that my picture is a little deceiving because the way that I've drawn it here, it almost makes it appear that the particle could exist in between this area, right in between. That is not true, not entirely true. Tunneling happens here, but we'll get to that in a second. Anyway, so I really like you to picture the box as just the potential well, as in actually just this. So that's the box that we're working with. And these are the different energy states associated with the different wave functions. Okay, so what on earth kind of wave function can we find that'll give us all of these conditions? Well, here it is. So you're going to have psi sub v of x is equal to n sub v times a polynomial function h sub v time is a function of y e to the minus y squared over 2. Okay, here is our polynomial. This is called a Hermite polynomial that's going to help us in having this ability for this to extend out larger as the box gets bigger. So that one satisfies, having this polynomial satisfies component number 2. Having psi go to 0 more slowly at farther displacements, that's going to be taken into account by the Gaussian here. And then, let's see. So then we have our normalization constant out in front, because we have to make sure that we do actually have a spring associated with this particular type of configuration. Okay, so now let's dive into how do you actually use this function. Atkins gives a table, I believe it's table 8.1, and these are called a list of the Hermite polynomials. So the Hermite polynomials are solutions to the following equation. So okay, so here's the solution, or here's the equation that they would be solutions to. So h sub v, this double dash here just means the second derivative, minus 2 times y h v prime, so that's the first derivative, plus 2vh v equals 0. So the Hermite polynomials are going to be equations that when you plug them in here, they're going to fit this, they're going to satisfy this whole equation such that this goes to 0. And when you take those Hermite polynomials, plug them in here, multiply them by the Gaussian and the normalization function, they satisfy the conditions that give us the boundaries of a spring. Rewind me and watch that a couple of times. This was the one that kind of gets really confusing as to how do you actually use this mathematics that you've probably never seen before. Fear not, it's actually quite straightforward. Look at table 8.1. So, 8.1, it says, when v equals any sort of integer, hy equals something. So, when v equals 0, this whole function equals 1. Cool. If v equals 1, hy equals 2y. If v equals 2, hy, or h is a function of y, equals 4y squared minus 2, and so on and so forth. So the cool thing is once you know, and you will always be given, what sub v value you have, now, well, I'll get to that in a second, all you do is you say, that's not that scary of a function. I'm just going to plug in 4y squared minus 2. That's something you've seen, that's something you've worked with before. So if we wanted to take the second derivative of 4y squared minus 2, so let's put this in. So we've got, actually that's not the example that I have. Never mind, I'm about to tell you about the recursion relation, but I'm also running out of time. Okay, let's see, what else can I tell you? Oh, Hermite polynomials, one of the reasons that they're nice, they are guaranteed to be orthogonal. As well, they have properties, again, that fit the harmonic oscillator. So in just a second, the next video, I will show you the recursion relation, and I'll teach you about how to move forward with the, actually no, go ahead and pause.